right, guys, we are going to pick up right after that lesson that we had on amplitude. So if you didn't get the amplitude lesson read with me on the virtual day yesterday, you need to go back and take care of that, all right? Okay, so we are going to start out looking at wavelength, okay? So right away, I see that there is a vocabulary word that I'm going to highlight. A wavelength. The wavelength of a wave is the distance from one point on a wave to the same point on the next wave, okay? The figure above shows how wavelength is measured for transverse waves and for longitudinal waves. To measure the wavelength of a transverse wave, you measure the distance from one crest to the next crest, or you can measure from one trough to the next trough. In the same way, both of these distances will be the same. Alrighty, so we could measure from crest to crest, that's your wavelength, or from trough to trough, that is your wavelength. To measure the wavelength of a longitudinal wave, you can measure the distance from one compression to the next compression, or you can measure from one rarefaction to the next rarefaction. In the same way, both of those distances will be the same. Wavelength is measured in units of distance, such as meters. We're going to go ahead and highlight that. It's a distance measurement, so it's going to have a distance unit of meters. All right, so come up here and let's take a look at that. So we have gone from one compression to one compression, or one rarefaction to one rarefaction. All right. Frequency. This is another property of waves, is called frequency. So I see a vocab word, so I'm going to go ahead and switch. The frequency of a wave is the number of wavelengths that pass by a point each second. So frequency is determined by measuring how quickly an object or material producing the wave vibrates. Each vibration of the object produces one wavelength. When the object vibrates faster, the waves will have a higher frequency. The frequency of a wave will be equal to the number of vibrations the vibrating object makes each second. So I'm going to clap my hands here. So we're going to have a very low frequency, okay? And then now here is a very high frequency. Okay? So the unit for frequency is hertz. So like we have meters for distance and liters for volume. Frequency is hertz. So how are wavelength and frequency related? Okay, the wavelength and the frequency of a wave are always related. When the frequency of a wave changes, the wavelength also changes. The figure above shows how frequency and wavelength are related. Notice that the wavelength of the wave on the left is longer than that of the wave on the right. Okay, so let's stop here. So look at the distance here. Here I see crest. Let's change it to that. Crest to crest and crest to crest. Okay, so this is longer here on this left-hand side compared to this one here on our right side. All right, so that's what that is referencing. Okay, waves with a longer wavelength have a lower frequency. Waves with a shorter wavelength have a higher frequency. So we're going to write here on the margin that they are going to be inversely proportionate. So we are going to have an increased wavelength. So what that means is the distance between these two is farther. We're going to have decreased frequency. But let's change this just so we can tell a difference. So, but if we've got a decreased wavelength, so the distance between these two crests is smaller, then that is going to be an increased frequency. All right, so they are inversely proportionate. So this one has a decreased wavelength, okay? The difference between these two, it's shorter compared to this one right here. We have a longer wavelength here. So the distance between crest and crest is longer. So that's an increased wavelength. So there's not going to be as many waves that happen per second as one that is shorter. Okay, so increased wavelength equals decreased frequency. Decreased wavelength equals increased frequency. Okay. Alrighty, so we don't have to go through this bottom section of calculating these wave frequency. We're not going to do that this time. So just make sure that you have that written at the top there, okay? All right. So wave speed. Different types of waves travel at different speeds. We're going to go ahead and highlight that. That's important. So you experience this when you have a thunderstorm. So during a thunderstorm, you might hear thunder a few seconds after you see lightning. Light moves more than 1,000,000 times faster than the sound waves you hear as thunder. So you'll see that crack of lightning, and then later, a few seconds later, you'll hear the boom of the thunder because the light speed is faster than the sound wave speed. Okay, so this is a part here that is on your study guide. All right, so waves traveling through different materials. It's actually on the very first part of your study guide in that first chart. The same type of waves travel at different speeds in different materials. Mechanical waves, such as sound waves, usually travel fastest in solids and slowest in gas. Let's mark that. Fastest in solids and slowest in gas. The table on the right shows the speed of sound in several different materials. Mechanical waves also usually travel fastest if the temperature of the medium increases. So we can just understand that if we have an increased temperature, we got a lot of kinetic energy going on in those particles, and that is going to increase the speed. Things are moving really fast when we've got a lot of kinetic energy and a lot of thermal energy. Okay, electromagnetic waves move fastest in empty space. So I'm going to go ahead and change that to a different color so we can differentiate. EM waves travel fastest in empty space and slowest in solids. Okay, so you can kind of take a look at this chart and you can see that the sound waves travel fastest in solids, mechanical waves travel fastest in solids here, and it's going to be slowest in gas. You can kind of see that, okay? So we're going to skip over this section on calculating speeds. We're not going to have to do that this time. So here are your vocab words, so continue to add them. So we're going to take a moment and highlight and fill in this graph. So if you like to stop this video and fill it out and then check with me, please do that, okay? So the top of this here, that's the crest. This is a transverse wave. And the bottom here, that is a trough. Okay, and the distance between trough and trough, that is your wavelength. And the distance from the rest to the crest, that is your amplitude. Okay? Alrighty, how'd you do on that? Okay, so we are going to scroll, and we're going to do just a little bit here with this first part of lesson 3. So it's how waves interact with matter. Waves interact with matter in many ways. Waves can be reflected by matter. They can change direction when they travel from one material to another. Also, as waves move through matter, some of the energy they carry can be transferred to the matter. Waves can interact with each other or work together. Two different waves can overlap or cross over each other. When this occurs, a new wave forms. The new wave has different properties from those of either original wave. All right, so we're going to be touching on all of these, reflection and that type of thing here, but we are not going to do this section. So this is called interference. So when we get to that section in our book, we're not going to cover that, all right? So let's take a look at absorption. So right away, I see that we have a vocab word, so I'm going to highlight that. Absorption is the transfer of energy by the wave to the medium through which it travels. So when you shout, you create sound waves. As the waves travel in air, some of their energy transfers to the particles in the air. The energy the waves carry decrease as they travel through matter. Absorption is the transfer of energy by a wave to the medium through which it travels. The amount of energy absorbed depends on the type of wave and the material in which it moves. Absorption also occurs for electromagnetic waves. All materials, let's change that, right guys? Okay, all materials absorb electromagnetic waves. So here's an example. Darker materials absorb more visible light than lighter materials, which is why it's a little warmer when you wear a dark shirt on a summer day. Another example of absorption is with tinted windows. So if you've seen that on cars, so it's going to absorb some of that sunlight and heat and make it so it's not so bright and hot inside your car. Okay? All right, so then we have transmission. It's not transmission like on a car, so when we go do this vocabulary, don't put an engine on here. All right, so transmission is the passage of light through an object. Light waves are absorbed by some material but can't pass through other material. All right, so we'll actually talk more about light waves a little bit later. So for example, you can see through glass. So you can see through a window, but you can't see through metal. You can't see through a wall. Metal absorbs almost all of the energy of the visible light rays. However, light waves pass through glass because it absorbs only a small amount of the wave's energy. So you can see through glass, you can look through a clear glass because that glass is only absorbing just a little bit of it, so you can see through still. Okay, we have another one called reflection. So I'm going to highlight that vocabulary word. Reflection is the bouncing off a wave off of a surface, okay? So when waves reach the surface of a material, they can also be reflected. Reflection is the bouncing of a wave off a surface. An object that reflects all visible light appears white. Okay, that's pretty cool. Let's go ahead and highlight that. An object, with a highlighter maybe. Okay. An object that reflects all visible light appears white. An object that reflects no visible light appears black. And we're going to talk more about this when we talk about color in chapter 4. All types of waves can reflect when they hit a surface. They're going to come in and bounce back. Okay, reflection causes waves to change direction. When you drop a basketball at an angle, it bounces up at the same angle, but in the opposite direction. When waves reflect from a surface, they change direction. Okay, they change direction, like the basketball bouncing off of a surface. So we have got this example here where we have got this ray, we've got this flashlight, and here comes the ray bouncing off this mirror, and it is reflected off here. So there are a few vocabulary words to talk about here, or just terms. This is the mirror that it's bouncing off of, okay? And we'll come back up to this, because this is our last section for today. Okay, so I am going to highlight the vocab word right away. The law of reflection states that when a wave is reflected from a surface, the angle of reflection is equal to the angle of incident. And this is due to the law of reflection. So let's read this little section and then we're done for today. The direction of an incoming wave that hits a surface and the reflected wave are related. A line that is perpendicular to the surface is called the normal. Okay, so that's this one right here. Okay, that's the normal. The angle between the direction of the incoming wave and that normal is called the angle of incident. The angle between the direction of the reflected wave and the normal, let's change that color, and not that one. Here is the angle of reflection. The angle between the direction of the incoming wave and the normal is the angle of incident, where it's coming in. The angle between the direction of the reflected wave and the normal is the angle of reflection. The law of reflection states that when a wave is reflected from a surface, the angle of the reflection is equal to the angle of incident. The figure above shows the law of reflection in action. Okay, so it comes in and bounces out at the same angle. So if this is 30 degrees, this is 30 degrees. If this is 40 degrees, this is 40 degrees, okay? All right. One thing I forgot to mention here with this transmission, or actually the reflection, is that this would be like a mirror, right? Or this would be like that chrome on a car, that shiny parts on the fender that appears shiny because of reflection. So go through your study guide now, and on today's page I have the questions that you are now able to answer. So hang in there. We've got this, guys, and I'll talk with you.